Cool. Hi everyone. Thanks for coming to this lecture. I'm Zhiting, a PhD student at the machine learning department. My research is basically about deep learning and deep generative models, and applications like text generation, all this stuff. So in today's lecture, we will discuss topics about building blocks of deep learning. So now we are in a series of deep learning lectures, right? And the last time, Eric has discussed the foundations of deep learning, including the basic concepts of deep learning and its connections with graphical models. In today's lecture, we will discuss these building blocks of deep learning. This is mostly about model architectures of deep learning models. And in the next two lectures, we will discuss mostly about inference and learning algorithms of deep learning, especially deep generative models like adversarial learning and variational inference in deep neural networks. And in the last lecture, we will discuss more advanced topics. For example, a unified view of deep generative models and other advanced topics. So today's lecture will be kind of lightweight because neural architectures are mostly about heuristics and intuitions. There is nothing that's really principled here. So yeah, in this lecture we won't see many equations or formulations. But in the next 2 or 3 lectures, we'll see more principled stuff, variational inference, adversarial learning, and their formal formulations. Yeah, so the outline of today's lecture, we will basically discuss 4 popular model architectures in modern deep learning techniques. First is the convolutional networks. And the second is about recurrent networks for sequence modeling. We will discuss key problems of recurrent models, like long-range dependency problem and the vanishing gradient problem. And we will introduce LSTM, which is designed to handle these 2 problems. And we will see recurrent networks applied in different domains, in different forms. And then we will discuss attention mechanisms. We will discuss these key components in an attention mechanism, including query vectors, key vectors, and value vectors. And we will see attentions applied in different domains on text data or image data. And in the last part, we will discuss transformer, which involves multi-head attention, a special attention mechanism which was proposed recently, and the relevant models like transformer for machine translation and BERT for text representation learning. Yeah, so let's take a look at the first part, convolutional networks. So we have seen these fully connected neural networks, right, or MLP as we call it. And the ConvNet is a variant of MLP. It's inspired by the human visual systems. In particular, it's inspired by the concept of receptive field. So as we know in human visual system, right, our visual cortex contains a complex arrangement of cells. And these cells are sensitive to particular subregions of the visual field. Right. And in ConvNet, the concept corresponding to these cells is local filters. We can see this is an example of ConvNet, and in this example, we can see 4 local filters here in different colors. And we will apply these local filters to sweep the whole images to extract the features of the whole image. These local filters turns out to exploit the strong spatially local correlations present in natural images. So ConvNet has 3 major architectural properties. First is sparse connectivity. Here's an example. So, for example, here this neuron, right, is connected to like these 3 neurons in the preceding layer. Right? It's not connected to all these neurons, so it's sparsely connected instead of densely connected. And the second property is the shared weights. These weights in the same colors are tied to have the same value. And the third property is as we go deeper in the network, we will get increasingly global receptive field for each of the neurons. For example, here this simple neuron, right, it detects the local features corresponding to these 3 neurons. But for this neuron, the complex neuron, it will pull the output of the simple neurons, and the effective receptive field of this neuron involves the whole neurons, right, in the first layer. So as we go deeper, we get kind of larger and larger receptive fields for each neuron. Yeah, and with these properties, it turns out that ConvNets can get a hierarchical representation of an input image. Here is an example. Given this image, right, we can see like different layers can produce different features at different abstractive level. So here, for example, the first layer can kind of like detect the low-level features, like the edge and other primitive features of an input image. And as we go deeper, we can get like increasingly more abstract and high-level features of the image. And in the end, we'll get the features that is suitable for classification and other tasks. Yeah, so this is a very simple and the basic introduction of convolutional networks. And along the years, ConvNets has evolved a lot. For example, now we have like AlexNet, right, which was proposed in like 2012. This is kind of the first application of convolutional networks in real large-scale problems, like image classification. And later on, we have VGG networks, which is deeper than AlexNet. And then we have GoogleNet, which is deeper and has a more complex architecture. And now we have ResNet, right, which is very deep, which can easily go beyond like 100 layers. All these models are widely used in practice, and I won't go into the details of these different models, but you can but there are like pre-trained models publicly online, so you can like just download these models and use them in your project. Okay, so this is the first part, convolutional networks. Very quick, because I believe most of you already know these things, right? But if you have questions, please feel free to interrupt me. Okay, let's go to the second part, recurrent networks. Yeah, so convolutional networks were proposed for like a spatial modeling, right? And the convolutional recurrent networks were proposed for sequential modeling. In ConvNets, we can see this computation as a single-step computation. The output depends only on the current input. We can see this computation as in this diagram. Given the input, like an image, we generate a label, like a single label. This is a single step of computation. Where in recurrent networks, the computation is like is indeed a sequence of computation. So each hidden layer and the output will not only depend on the current inputs, but also depend on previous states of the hidden layers. We can draw this computational diagram, kind of like, and if we unroll this diagram, we can see the computation like this. at the first step, we take in the inputs and compute the hidden state and the output, right? And then the hidden state of this step will be fed to the next step, and together with these inputs, we get the hidden state and output of the second step. And this process goes on, right? And we get a sequence of like these different steps. Yeah, this is the computation of recurrent networks. And RNN is used for like sequence modeling, right? And there are different forms of like sequence modeling. The simplest form is again the one-to-one problem, right? For example, like image classification. This is the same as the use case of convolutional networks. So the input is an image, and the output is a label, for example. And we can do like a one-to-many problem. For example, in image captioning, right? We want to generate a sentence to describe an image, right? So the input is a single image, and the output is a sequence of tokens, which consists of a sequence of tokens, right? Which is the sentence to describe this image. And also we can do like a many-to-one problem, like sentence classification or like a video recognition. So the input is a sequence of like a tokens, right, or a sequence of frames in a video, and the output is a single label, for example, a sentiment label. And we can also do like many-to-many problems. For example, in machine translation, right, the input is a source sentence, like for example in English, and the output is another sentence, like in French, right? We call this problem, we usually call this as a sequence-to-sequence problem. And the second form of many-to-many is like this. We call it sequence tagging. The task is to like assign a label to each of the tokens, each of the input tokens. For example, in named entity recognition, right, we want to assign a named entity label for each of the tokens. Yeah, so these are different application forms of recurrent networks. Then let's take a look at training of recurrent networks. Here's a computation diagram of a recurrent network. So for each hidden state, right, to compute this hidden state, we'll use the hidden state from the last step and the current input, right? And we get this, we compute this in this way. And this red arrows denotes the gradients in backpropagation. It turns out that computing the gradients of H0 of this quantity involves many factors of W, the parameters in the recurrent network, and the repeated tangent H function. Yeah, so the problem here is that it can be shown that if the largest singular value of this matrix is larger than 1, it turns out that it will lead to an exploding gradient. Because here we kind of repeatedly multiply this W on the gradient, right? And at this step, we'll get kind of like the gradient will like goes very large, and we'll get an exploding gradient. We can address this problem with a very simple trick by gradient clipping. This is by like scaling the gradient if the norm is too big. Is too big. And on the opposite side, if the largest singular value is smaller than 1, then we'll get a vanishing gradient. The gradient will like go to 0 very quickly, and this makes the training very slow and ineffective. Yeah, so this is a key problem of recurrent networks, vanishing and exploding gradients. For more details, you may refer to these two classic papers. Yeah, so the second issue of recurrent network is the so-called long-term dependency problem. Let's see this example. The input is like I live in France and I know, right? And we want to predict this token. Right? The answer should be like French, right? Because of this context, like France. I live in France. I know French. This task is easy for recurrent networks because like this slot is very close to this context, so it's easy to model this dependency. But what if we like add more tokens in between, like I live in France and I know, right? So the distance between this context and its slot will be larger, right? And this makes the problem much harder because the model has to like model this long-term dependency. Yeah, this is the second issue of sequence modeling, long-term dependency problem. With these issues, like the vanishing gradient problem and the long-term dependency problem, here we come to LSTM, long short-term memory. So LSTMs are designed to explicitly alleviate these problems, including long-term dependency and vanishing gradients. So we have seen these standard recurrent networks. Right? This is computation, which is pretty simple. And for LSTM, the architecture is more complex. Let's take a closer look at this architecture. An LSTM basically includes a few like gate functions that make decisions of like reading and writing and resetting information inside the cell. For example, here the forget gate is used to decide whether to erase the cell, and we have input gates to decide whether to write to the cell, and we have an output gate which decides like, how much to reveal the cell to the outside. More specifically, the forget gate is used to decide like what must be removed from the hidden state of the last step, and the input gates decide what new information should be stored in the cell. We can see this case will depend on the hidden state of the last step and also the current input, right? And with these two gates, we can update the cell state with this function. Basically, we multiply the forget gates. We multiply this forget gates with the hidden states of the last step, and this basically decide like decide what information should be should be forgotten, right? This is the forget gates, and this is the input gates. Input gates decide which value should be like updated and scaled in this in the current state. Yeah, with these updated states, we can then next step is to decide like what information should be output from this cell. Right? We use the output gate. So this sigmoid function will decide like which part of the cell state will be revealed to the outside. Yeah, so with this computation inside the cell, we can see that LSTM has a much cleaner backpropagation compared to the standard recurrent network. So it turns out that there's no multiplication with matrix W during backpropagation. And instead, this gradient is multiplied by different values of forget gates. Right? So this makes the gradient less prone to like vanishing and or like exploding. Right? But of course, if the values of the forget gates are always like larger than 1, right, we'll still get like exploding gradients. Or if the values of forget gates are always like smaller than 1, then we'll again get the vanishing gradients, right? But these cases are not like not very often. So basically LSTM can alleviate this problem, this vanishing and exploding gradient problem. Yeah, with LSTM, we can do better sequence modeling and kind of provide a reasonable performance on these different sequence modeling tasks. But actually, recurrent networks are not limited to only these very simple and straightforward sequence modeling tasks. Indeed, they can be applied on different tasks with different input data. For example, here we have bidirectional recurrent networks. It's basically stacking two recurrent networks together, and the hidden states of the bidirectional recurrent network is the concatenation of both forward and backward hidden states. And this allows the hidden state to capture both the past and the future information for each of the steps. And we have tree-structured recurrent networks. Here, hidden state of this tree-structured model will depend on the inputs and also the hidden state of its children, right? And we can see the standard sequence LSTM as a special case of the tree-structured LSTM by seeing that each node has exactly one child, right? This is a special case of a tree-structured LSTM. We can also apply recurrent networks for 2D sequences. For example, to model the pixels in an image, right? We can use convolutional networks to do this modeling. For example, to predict this pixel, right? We can use a CNN to extract features of its neighboring pixels and predict this pixel. Right? This is the ConvNets. We can also use a row-based LSTM, which kind of model these pixels row by row, right? And to predict this pixel, we will condition on the preceding rows and the neighbor pixel. Or we can organize these pixels in a grid, and to predict this pixel, we'll condition on these pixels in a grid. Right? This is the diagonal by LSTM. And even further, instead of these predefined or fixed topologies, right, we can apply a recurrent network for graph structures, where the structure can be dynamic or even evolving over time. This kind of model can be used in image segmentation, because here each regions in the image are these regions are kind of irregular, right, and can evolve over time. So this model can be applied here. Yeah, this is a very quick overview of the different application scenarios of recurrent networks. Yeah, we have gone through these topics of recurrent networks, including this long-term dependency and vanishing and exploding gradients, and the LSTM model, right, which was designed to address these problems. And also we have seen these RNNs in different forms, right? So any questions so far? Yeah, cool. I think these topics are very, very, very basic, and I believe most of you already know these things. And the third part, attention mechanisms. Okay, so let's first take a look at some application examples of the attention mechanisms on different data like images and text. So here, this is an example of image captioning. The task is to generate a sentence to describe an input image, right? And we apply a attention model to this task. So attention mechanism is used to like choose which feature to pay attention to during the prediction. For example, in this case, right, the model will generate this sequence, right? And when generating this token, frisbee, the model will attend to this particular region in the input image, right, to capture relevant features from the image. And here, for example, to generate a stop sign, right, the model will attend to this part. And here, like to generate the people, right, it will attend to this region. And here, to generate the cheese, right, the model will attend to this background of this image instead of the foreground object. Yeah, this is the application of attention on image data. We can also apply attention on text data. For example, in machine translation, right? The input is a sentence, like in English, and the output is a sentence in the other language. And here is the attention of the model. We can see like when generating this token like zone, right? The model will attend to this particular input token area, right? And to generate this token, it will attend to this European, right? Yeah, so basically attention helps to like choose which feature to pay attention to when during the prediction. So why would we use attention? The first reason is that again the long-term dependency problem, right? So here is a standard sequence-to-sequence without attention, right? For machine translation. Right? To generate this token, right, the model has to find this relevant input token, right? And we can see this dependency is really the path is very long, right? This makes the problem very hard to address because of the long-range dependencies. But with attention, we can see the model can directly like depend this prediction on this token, right, through this attention path. So this kind of like make the dependency path much shorter, and makes the problem easier, kind of. And the second reason is that attention enables us to learn fine-grained representations of the inputs instead of a single global representation. So here is the standard sequence-to-sequence again for machine translation. So given an input sentence, right? In standard sequence-to-sequence, we will get a single factor to represent this input sentence, right? Using a decoder, right? That means this one sentence will correspond to a single representation. But with attention, the model can attend to smaller parts of the data. For example, like patches in an image or like words in a sentence. And when generating different tokens, it will attend to different parts. So this basically allows a different representation of the single input in different phases in the inference process. Right? So this makes the kind of like makes the model more powerful to like extract better features, kind of. And the third reason is that attention provides improved interpretability. Again, like here, like if we for machine translation, right? If we like visualize these attention results, we can see like we can somehow see like why the model will generate this token, right? This is because of this token, right? So this kind of provides some explanations of the outputs. Yeah, so let's take a look at the computation in attention mechanism. Let's take the attention, take the machine translation as an example. So given an input sentence, right, we first use an encoder to encode this sentence and get the hidden state, right? So here, assume we have 4 input tokens in the input sentence, and we get 4 hidden states, right? Or we get 4 encoder states. We can consider these vectors as the key vectors. And during decoding, right, for this step, we use these decoder states as the query vector to compute the relevance of this query vector between each of the relevance between this query vector and each of the key vectors, right? And we somehow get these scores, or we call this as alignment scores, right? And then we apply a softmax function on top of these alignment scores and get a normalized distribution, which we call as like attention distribution or attention weights. Right. This is the first step by using a query vector to compute the alignment score with the key vectors, right, and compute the normalized distribution, which is the attention distribution. And the second step, we see this encoder state as the value vectors, and we compute the weighted sum of these value vectors using this attention distribution, and we get this output state, which is used in the decoder to generate the next token. Yeah, so basically, attention computation will involve 2 major steps. The first step is to use a query vector to compute the alignment scores and the attention distribution with regard to these the key vectors. Right? Here in machine translation, the query is the decoder state, and the key is all like encoder states. And the second step is to use this resulting attention distribution to compute a weighted sum of the value vectors. Here, value vectors are the encoder states. Yeah, this is the computation of attention on text data. And there are many popular attention mechanisms with different alignment score functions. As I said, like alignment score will depend on the query and the keys, right? And we can see like with different, we can use different functions to compute this alignment score, basically. Yeah, and the attention can also be used on image data. Right? For example, here, this is for image captioning. Given this input image, right? We first use the convolutional networks to extract these feature maps, and then we see these feature maps as the key vectors here, right? And to generate this caption, we set the query as the decoder state, just as we did in machine translation, right? And we can compute the alignment score between these two, and again we use the feature maps as the value vectors, and we compute the weighted sum of these value vectors, and then we can generate these tokens. So in this work, the authors tries different attention methods, like hard attention and soft attention. So soft attention is what we have seen in machine translation and in the last slides, which is to like compute the weighted sum of the value vectors. An alternative way is that we can like first sample a value vector, right? According to this distribution, right? And then we generate this token conditioning on this sampled vector. This is called a hard attention. And here are visualizations of these different attention methods. The first row is the result of soft attention. We can see like to generate this token, right, BERT, the model will attend to this region, right, which is kind of like a soft and kind of scattered. And for hard attention, the model will like focus on very small parts in the image. Right? And I believe that soft attention is more widely used in these days. So hard attention is not really popular. Yeah, and besides image captioning, which is to generate a single sentence to describe an image, we can also apply attention to the task of image paragraph generation. The task is to generate a long paragraph to describe an image. Right? So this is no longer a single sentence. This is a long paragraph. And the problem here is that we have to handle this long-term visual and language reasoning, right? Because we want to generate a long paragraph instead of a single short sentence. And to make sure we can generate the content for description, right? We have to ground each sentence on the visual features, right? For this grounding, we can use the attention mechanism to do this task. So in this work, we propose this pipeline. In the first step, given the input image, right, we first detect the semantic regions of the image. For example, here we have this region, right, in blue. And for each of the regions, we use an image captioning model to generate a local phrase for each of the regions. For example, here, given this region, right, we can generate a phrase like a man wearing white shirt and pants, right? So with these regions and the local phrases, we can apply a attention on both the regions and the phrases, right? And the resulting features will be fed to the generator to generate the paragraph. And the generated paragraph will be fed to the discriminators for further supervision signals. This is what we call the multi-level adversarial learning. But I want to dive into these details because adversarial learning is the topic of the next two lectures. Yeah, so with this pipeline, we can get very sensible results. For example, here, right, given this image, right, we first detect these regions. And for each of the regions, we get the phrases. Like here, this large region, right, we get people riding a bike. And for this blue region, we get man wearing a black shirt, right? And the resulting paragraph is kind of like a combination of these phrases into a coherent and long paragraph. Like here, first sentence, right? A group of people are riding bikes. This model is basically attending to this first phrase, right? And this region, right? And the second sentence, there are two people riding bikes, blah blah blah. So this is basically the second sentence, right? Yeah. So this is the attention on image paragraph generation. Yeah. So this is the third part, attention mechanisms. We have seen that the key components of our attention mechanism is three parts: the query vectors, the key vectors, and the value vectors. Right? And we see attention can be used in both text data and the image data. Right? Yeah. Any questions so far? Okay, cool. Okay, let's move on to the last part, transformer model, which is based on multi-head attention. Yeah, so multi-head attention is a new technique, kind of proposed in recent years, and this technique has been used in different tasks, like machine translation, pre-trained text representation, and language models, right? And all these applications have produced state-of-the-art results on these different tasks. So what is multi-head attention? It starts with this simple scaled dot product attention. We have seen this in previous slides. Again, right, with these query vectors and key vectors, right, we first compute this attention distribution. And with this attention distribution, we can compute a weighted sum, right, of these value vectors. Right. This is the base attention mechanism. And the multi-head attention kind of like use multiple attention distributions and the multiple outputs here. It kind of like copy this attention for multiple times, so that you can get different multiple outputs here, right? Given this single input, key value, key, and query. And the multiple outputs will be like concatenated, and then and we'll go through a linear layer to combine these multiple outputs into a single output. Yeah, this is the multi-head attention. And this attention is usually used as a building block in this larger block. We can here with the input will be fed into this multi-head attention, and then the addition and the normalization, and then it will fed to the feed-forward layers, and again like addition and the normalization and the outputs. Right. This is the basic building block in a transformer model. And with this building block, we can like construct encoder and decoder in a machine translation model, which we call as like transformer. Right. In particular, in the encoder, we'll set these query and key and values to be the encoder states. So this is kind of like the encoder will attend to itself. We call this as a encoder self-attention. And similarly, in decoder, we'll set like a query value and the keys to like the decoder states. So it's kind of like the decoder will attend to itself. So this is called decoder self-attention. And again, between encoder and the decoder, we will apply attention by setting keys and the values as the encoder states, and setting query as the decoder states. Right? This is the same as in the standard sequence-to-sequence model. Right, so with these three attentions, this model can produce very impressive results on machine translation. Indeed, this model is the state-of-the-art model for machine translation. Yeah, this is the first application of multi-head attention on real tasks. And the second application is the BERT model, which is a pre-trained text representation model. So for text representation, right? We all know that we have this like conventional word embedding method, right? For example, like a word to vector and a graph, right? These are pre-trained word embedding method. This method are essentially a pre-trained matrix, right? Where each row is an embedding vector of a word, right? This is, for example, this is the a conventional word embedding matrix. And given a piece of text, right, we'll use this word embedding to like get the representation of the text by simply replacing each token, right, with its corresponding embedding vectors in this matrix, right. This is the conventional word embedding method. And what is BERT? BERT is a model to extract or contextualize the word embeddings. So BERT is no longer a simple matrix. Is a very complex model. It involves like many layers of encoders, right? And given an input sentence, right, it will we feed this sentence into the BERT model, and with like a very complex computation like attentions and different nonlinear functions, right? We'll get this representation for each of these tokens. And here, each layer is the basic building block we have seen this in transformer. So basically, this is a very large transformer encoder, kind of. Yeah, and we can see we can just treat this BERT model as a black box model, and we can apply this for like a text representation and the downstream tasks like sentence classification. Right? Given an input sentence, right? We first append a special token here, and we get the representation, the vectors of each of these tokens, and then we use the vector representation of the special token as the feature, and we input this feature to a sentence classifier to get the label. You know. This is a use case of BERT for downstream tasks. Yeah, and with this method, we can get huge improvements over state-of-art models on like 12 NLP tasks, including like sentiment classification, like question answering, and like natural language inference, all these different tasks. Yeah, so as in a conventional word embedding method, right? We have to like pre-train this model, like pre-train this BERT model on very large data sets. So as we have seen, like this model is basically a very big transformer encoder with over 200 million free parameters to learn. And the training data, for training data, we use a large Wikipedia corpus plus a collection of free ebooks. And the training procedure is like this. The first objective is what we call the masked language model. The intuition here is that we can like mask some percent of words from the inputs, and we ask the model to reconstruct these words from the context. Here is a visualization of this procedure. Given this input sentence, right, we first mask out some of the tokens in this sentence by replacing this token with a mask token, and then we get the representation of the tokens, right? And we train the model to reconstruct this original token, given the vector representation of this mask token. Yeah, this is our first objective, and this task is basically based on a single sentence, right? And the second objective is about the two-sentence task. This task is used to enable the model to understand the relationships between sentences. So, and the idea is that we concatenate two sentences, A and B, right? And we want the model to predict whether the sentence B actually comes after A in the original text. This is the procedure. Given two sentences, A and B, right? We concatenate them together, and we input these two sentences into the BERT model. And we want the model to predict whether this sentence really comes after this sentence in the original text. Yeah, with these two objectives, we can and with this large data set, we pre-train this model. Because this model is very large and the data set is very large, right? It turns out that training pre-training a BERT model on 4 GPUs will take like 4 days. But if we train this on a 4 GPU desktop, it will take like around 100 days. So you can see the amount of computation, right, to pre-train this large model on a large data set. Yeah, so yeah, we have seen these large models and the different like pre-trained methods, right? And fortunately, despite this large amount of computation, these models are pre-trained, and the pre-trained models are public online, so you can just download and use them in your project. And to enable ease of use of these techniques, we release a toolkit, Texar, which is a general purpose text generation toolkit on TensorFlow. And in Texar, we provide many like components like encoder and decoder with different attention mechanisms. And for example, like word embedders, right, and the classifier, right? And we provide different loss functions and different data modules and the training procedures. And with Texar, you can like easily construct whatever model you want, especially for text generation. So here, for example, are to use a word embedding, right, in your model, right? We first like read the data, right, and load the pre-trained word embedding matrix, right? And we construct a word embedder instance. You initialize this instance with the pre-trained embedding matrix value, and we can configure this word embedder. And then we input the sentences into the embedder together embedding vectors. And then with these features, right, we can feed these features into a classifier to do like a prediction, like a classification of these different tasks, right? And you can easily like switch between like word to vector and graph by just like configuring this configuration. Like here, you will specify the pre-trained model checkpoint kind of. And you will specify this read function to like switch between like a word to vector and the graph. This is the conventional word embedding on Texar. And what if we want to like use BERT instead of this conventional word embedding? Right? Yeah, here we can keep this data loading part the same. And we replace this word embedder with the BERT model, right, which is a transformer encoder. And then we can load the pre-trained checkpoints from the file, right, to initialize this model. And again, like with this embedder, right, with this BERT embedder, we just input this sentence into this embedder and get the embedded vectors, and again, we can use these vectors to do like downstream tasks, like classification. Yeah, this is word embedding or like a text representation on Texar. And on Texar, we can also like construct this sequence-to-sequence attention very, very easily. Like here, this is an example of machine translation. Again, we first read the data, right? Machine translation data. And we construct a decoder, right, to decode the sentences into the hidden state. And then we use a decoder, right? Here we can construct the attentional decoder to generate the sentence. And then we can compute these loss functions, right, for the model training. And here we can configure this decoder to have like different cells and different attention mechanisms. For example, here we can like use a LSTM cell, and we can specify the number of layers, right? And we can specify the attention mechanism. Like here we use this attention, right? And we can specify the size of this attention. Yeah. So with Texar, you can like build a machine translation model within like 20 lines of code, kind of. Okay, so this is pretty much I want to discuss today. The key takeaways is like the key takeaways here are first we discuss the convolutional networks, and then recurrent networks, right? LSTM was designed for long-range dependency and vanishing gradient problems. And the recurrent networks are not only for sequence data, it can be used in different domains and different tasks, and to model like 2D sequences, to model like trees, or to model like graphs, right? And the third part, attention mechanism. The three core elements of the attention mechanism is the query and the key and the value, right? We use the query and the key to compute the attention distribution, and use the attention distribution to compute a weighted sum of the value vectors. And there are many different variants based on different alignment score functions. And we have seen this attention applied on different domains, like text data, like image data. And in the last part, we see this transformer model, which involves the multi-head attention mechanism. A transformer model is for like machine translation with the encoder and the decoder architecture. And the BERT is basically a transformer encoder for like used for text representation. And the GPT-2 is a pre-trained language model. We haven't discussed this in this lecture, but it's also based on multi-head attention. It's basically a transformer decoder, right, for language modeling, kind of. Right, and we see like with Texar, you can like build all these different techniques pretty easily using Texar's API to build whatever model you want. Okay, yeah, this is pretty much this lecture. So, any questions? Okay, nice. Yeah, as I said, this lecture is pretty lightweight because all these things are just heuristics, and there are no like principled stuff, kind of. But starting from next lecture, we'll see many like principled like formulations and different kind of new insights into these different models, especially deep generative models. Okay, cool. Then see you next time.